Okay. Today, here we are, Friday, first day of spring break, and yes, it's time to get some physics done. All right, this is coming to, it's the chapter that I both love and I hate. Not love to hate or anything else. It is one of the harder topics to try to explain. It's one of the most important topics in the history of mankind, I would say. If you have the basic idea of this is what happens when we have, how can we make currents? How can we make potential using magnetic fields and electric fields? Okay? How does a magnetic field affect an electric field? How does an electric field affect a magnetic field? Well, what we're going to do, okay, first thing we want to discuss is what happens if we put a bar magnet into a coil of wire. So now, if I do that, some interesting things happen. Okay? Remember, if I put, if I had an electric field, like
Ms. Ciccarelli, please dial 1200. Ms. Ciccarelli, 1200.
if I had a current going through a wire, okay, a magnetic field is produced. Okay, so we can see how an electric field inside the wire creates a magnetic field. Well, the reverse, we want to see how that affects, okay, how that occurs. So now, if I have something like this, I have a magnet that I put into a, and I'm just going to use the diagram that they have in your book, okay? Just a little coil of wire here, and it's connected to some sort of little device here that can measure either EMF or potential or the current. Okay? What happens is, okay, I have a magnetic field that's coming out of here, like this, and it kind of loops back in, assuming that this is the North Pole and this is the South Pole. Okay? So as this comes in, the magnetic field is going to start entering that coil. Well, if the magnetic field starts entering in, okay, very interesting, a current is produced inside this loop. Okay, let's put in a little, what do they call it, ammeter. The ammeter there. So they have a little ammeter put in here that can detect the current. Now, interestingly enough, okay, if I push this North Pole into the coil, current will be produced in one direction. If I take this bar magnet and I rip it out, current is produced in the opposite direction. Very interesting. But if I just leave the magnet inside this coil of wire, nothing happens. And this is where Michael Faraday basically became one of, maybe the greatest experimenter of all time. He tested all sorts of different arrangements, and what he was able to determine was that it wasn't the magnetic field itself that caused the current in here. It was a changing magnetic field that caused a current inside there. He said, if you change the number of magnetic field lines inside a coil of wire, okay, you will produce a current. Okay? Now, another setup, and this is shown on page 792 of your book. Okay. If I take a little ammeter here, okay, and connect it, and I've got a little loop here like this, okay, and over here I take another little loop, do like this. I'll just get them very close to each other. And I don't have the equipment to do this right now, so you're just going to have to use your imagination. Okay? And now to this, I connect a battery. And let's just say I make a switch here. Well, now, interestingly enough, okay, initially, you know, these two assume to be that they're parallel. If you want a better picture, you can look at the book on page 792. Something interesting happens. I close this switch, current comes out, okay, and And for a very brief moment, current is produced inside here. Then, if you want to put a resistor in here too, so that you don't short circuit out and you have too big of a current. But okay, I close this switch. Current will go around here, and this current in here stays regular. The current in here just appears for a moment, just a moment. Goes away. Well, interestingly enough, okay, I have the current connected now. I open the switch back up. Current is now produced in the opposite direction, very briefly again, goes away. What's happened is that I've induced a current between these on this one. Because when I turn the current on, okay, I created a magnetic field. Okay, current is runs through here. Okay, current will produce a magnetic field. Well, I started off at 0, and then my magnetic field was something. Okay, going back to what we did last week, we get with the magnetic field from with the wire. Okay. Well, that magnetic field registers over here, so it goes from 0 to something, and had to take a little bit of time to do that. So there was a very brief moment of time where the magnetic field changed. It went from 0 to something, but it had to go through that. It had to change to go from 0 to that something. Well, this coil wire over here notices that there's no magnetic field, then there is something. Okay? And what happens here is that a very slight current is produced over on this side. Okay? For a brief moment in time, just while it changes. Okay? Again, magnetic field that's produced over here occurs only while it's changing. All right. Now, one of the things, and this is where we're going to get into Faraday's law. Okay, and there's actually, it's a combination of Faraday and Lenz. For Heinrich Friedrich Lenz, we developed a book calls it a rule, now known as Lenz's law, that you put these two together. And it's probably one of the most important things that has ever been devised by humans. We wouldn't have generators, okay? And without generators, we don't have anything that we have now. The 19th century, and the difference between the 19th century and the 20th century is almost all due to this change. Okay? You look at the difference in a household in 1875 and 1975, it's almost all due to this. Okay? So I don't want to overstate how important it is, but I don't think I can. Okay? I think it's virtually impossible to overstate how important this concept is. Okay? Not so much to the breadth of the E&M exam, but to society, essentially. Okay? Now, the rule that Faraday was able to come up with, or law, it has to do with the changing magnetic flux. Okay? Now, we talked about electric flux, phi, which was the integral of E dotted the area. Okay, and we're looking over a closed surface. It doesn't have to be a closed surface. Shouldn't say that. Okay, but flux in general, okay, is E dot dA. Now, for a magnetic flux, I just want to make sure I didn't talk about closed loops here. For magnetic flux, it's the same thing. If electric flux is E dot dA, what do you think magnetic flux is going to be? B dot dA. Okay? It's the amount of magnetic field that goes through an area. Okay? That's all it is. Electric flux, same idea. It's the amount of electric field that goes through a particular area. Now, If I'm able to keep it simple, I can make that B times A. If the dot product, if the magnetic field is constant, okay, my magnetic field is constant, points in the same direction at all times, and stays at 90 degrees, 0 degrees from the area vector, this would give me B times A. Okay? And that's where we're going to try to keep it for the most part, is B times A. Okay. Now, the unit for magnetic flux, by the way, is the Weber. Probably in the original German it's Weber or something like that, but unit for flux, you're going to have, you just added, this integral is just adding areas, so that's just meters squared. So we have Tesla meters squared, okay, that's equal to the Weber. Okay. Now, Faraday's law says this. Everybody talks about E equals mc squared, but this is probably the most transformative equation between the 19th and 20th centuries again. And part of it is due to, part of this is due to Faraday. The other part has to do with Lenz. Okay? Lenz essentially contributes right there. Lenz's law pretty much contributes that.
Oh, sorry.
Now, okay. So now, what this says is that a changing magnetic flux will create an electric potential, okay, an EMF. Okay? Now, if I put in many if I put in multiple coils, okay, multiple turns, I can use is equal to negative N dpb dt. And yes, I really like this equation, not only because of its importance, but I really like saying E equals dpb dt. It just kind of rolls off the tongue. Now, about that negative, okay? Magnitude all contained within here. Okay? This is Faraday. This is Lenz, and that's a very important one as well. Okay? Now, maybe not so much the society, but it does help us understand physics a little bit more. You can think of magnetic field as the Republican field. It does not like change. Okay? What this does, okay, this negative is opposing change. Okay? Please don't take that as a value judgment on Republicans or Democrats making change or anything else like that. Just help you keep it in your mind. That negative just helps us understand that whatever's happening, it's trying to oppose the change that occurs. So let's go back to that first picture, okay, where we had a little ammeter here. We had current, and now I have this magnet that's coming in here, okay, and it's going to produce a magnetic field that's going to enter in that magnetic field is entering into this wire. Now, and I should do this. Okay, so this is coming in through here. Okay, here's my coil. It's going in through like that. I was looking at a side view. Okay, my okay, the bar magnet would be entering in this direction. Now, what this is saying, what the negative is saying, is that we're going to try to oppose that magnetic field that's entering in. So now, I have what's happening here, and really take your time to think about this. As this magnetic field enters in, I'm getting more and more magnetic field entering into the coil, okay, going in that direction. A current is going to be introduced in here that will try to oppose this. Now, let's think about this. Okay. I have a magnetic field that's increasing going in that direction, so I want to create a magnetic field, a current in this wire that will create a magnetic field that points in that direction. So now, as I do this, okay, I go around, no matter where I go, if I want a magnetic field that's going into it like this, okay, I'm getting a current that will flow, and you have to understand the perspective that I'm looking at, a current that will flow in that direction. Okay? Because what's happening, okay, as I go around, my magnetic field is going into, going in this direction. Okay? Another way you can think about it is, if I'm going around this loop like this, okay, I wrap my fingers in the direction, the other right-hand rule, I wrap my fingers in the direction of the current, my thumb points in the direction of the magnetic field. Okay? The direction of the induced magnetic field to try to oppose this magnetic field. Now, I take this north pole out. I probably should label this north, label this south. Now, I have these magnetic field lines that are pointing in this direction. Just take current out. Now let's just say for the time being that the magnet is just staying there. Okay? I should talk about this first. The magnet stays there. There are no magnetic field lines that are coming, additional magnetic field lines that are coming in or going out. Okay? I have the same amount, a static amount. This lights that. Okay? Nothing happens. It's only when a change occurs that something happens. So now, I take this magnet and I pull it away. So now, I have a magnetic field that is going in this direction, but it's decreasing. I have all these, okay? I have magnetic field lines that are going like this into this wire, but now I'm slowly starting to reduce that number. Okay, I pull one out, and then this one gets a little shorter. Okay, so the magnetic field in here is getting weaker. Again, it opposes the change. So if that magnetic field lines are coming like this and they're getting weaker, okay, in order to compensate, a magnetic field should be created inside here. This will be my B induced by a current, okay? This will try to pick up the slack. Now, if it's going to go like in this direction, fingers wrap around in the direction of the current, okay? And so it'll go like this, back in here, and out over here. Okay? So that's why it goes in opposite directions when I shove a magnet in and I pull it out. We'll talk about this when you guys come back on Wednesday. Okay? Now, that's through 30-4. We will stop there. More to come. Don't worry, more to come.